So today the topic we will be discussing is the waveguide, and it is the rectangular waveguide. So actually, what we know about waveguide, if we want to transport water, then we need to use some pipe, a hollow pipe, so that we can transport the wave, so that we can transport the water. And in the world of microwave and the radio wave, radio and waveguide is their pipe. This is the pipe by which we can transport our waves from one place to another. It is a hollow metal tube that guides the electromagnetic waves from one point to another point with the minimal amount of losses. So why we use the waveguides? The main purpose of using the waveguides, or the features of the waveguides, are it is a high frequency signals, and there is no center conductor. That means these are the hollow type, and there are TM modes and TE modes in a waveguide. So now let us delve into what is rectangular waveguide. So this is a picture of rectangular waveguide, and these are the practical pictures. Practically, the rectangular waveguide looks like this, as the shape of the outer part, or the opening and the closing part of the shape of the opening and the closing part of the rectangular waveguide is a rectangular shape. That means that is why this type of waveguide is called rectangular waveguide. So why we use a rectangular shape waveguide? Because it is very easy to manufacture, and it is very easy to analyze. Then the dominant mode, the TE10 has the TE10 mode here is the dominant mode, and it has the lowest cutoff frequency and making it very efficient. And there is a standardized hoist for the simplified design, and that is why we use the rectangular waveguide. So previously we have learned about the parallel plate waveguide, and now we are working with the rectangular waveguides. So what is the main difference between the parallel plate waveguide and rectangular waveguide? Actually, parallel plate waveguides has the two flat metal plates. There are two flat metal plates. If we can look at the picture of parallel plate waveguide, then we will see that. So this is the picture of parallel plate waveguide, or this one. So in case of parallel plate waveguide, there are two flat metal plates, and they are kept with a distance. And in case of rectangular waveguide, we can see that there is a rectangular shaped enclosed rectangular metal tube, and that is why there's the main structural difference between parallel plate waveguide and the rectangular waveguide. Then parallel plate waveguide supports the TEM, TE, and TM mode. That means the transverse electromagnetic mode, the transverse electric mode, and the transverse magnetic mode. But in case of rectangular waveguide, we can only it only supports the transverse electrical and transverse magnetic. It does not support that TEM. The TEM, that means the transverse electromagnetic wave. And in case of field confinement, the field confinement in the parallel plate waveguide is very weak, and the field actually spreads out in other places. And in case of rectangular waveguide, as the shape is rectangular shape, and the passing the waveguide is very easy. That is why it is very strong. And in this case, the field confinement is strong. That means the waves are confined within the field. The practical use, in case of practical use, rectangular waveguides are in case of practical use, the rectangular waveguides are used much more than the parallel waveguides. And the applications, there are many applications of parallel waveguides in our day-to-day life. We can see the use of uh, rectangular waveguide in radar system. The waveguides handle the massive power pulses in the military and weather radars. And then low loss transmission for this is used for the low loss transmission for space signals or satellite communication. Again, with rectangular waveguides are used for medical imaging. The MRI machines use this kind of waveguides. In the research labs for the waveguides and other microwave research purpose. Usually, this type of waveguides are used much more than the other type of waveguides. And again, in the 5G networks, when the frequency is more than 28 hertz, 28 gigahertz, then we can use the rectangular waveguide for this. Now we come to the theoretical parts. Here the rectangular waveguides are the earliest type of transmission lines used to transport the microwave signals. That means these are the earliest types, and couplers, detectors, isolators, attenuators, and slotted lines are commercially available for various standard waveguides. Waveguide bands from the 1 to 220 gigahertz. So at first, let us analyze the TE modes. the structure and the mode. In case of the structure and the mode, let's start with the TE mode. As we do not have the TEM mode in this case, then we will analyze the cases for the transverse electric mode and the transverse magnetic mode. The TE waveguides modes are characterized by the fields Ez equal to 0, here Ez equal to 0, and Hz must satisfy the reduced waveguide equation. And that's why you can see that this is the main equation, the del square, del x square plus del y square plus kc square is constant, and this is the Hz, the value of magnetic field in the jet plane. And analyzing this, solving this equation, we get, and substituting the, and then we have Hx equal to the Hz of xy, this x component and y component, and replacing the this and this equation, we get this equation. And after that, solving the equations and solving both of the equations, we get the main equation, the general equation for the Hz can be written as solving the general equation for Hz. That means the main equation for the magnetic field here is the xy, that a cos kxx plus b sin kxx into c cos kyy plus d cos kyy, and these are the constant terms for a, b, c, d. So these are the constant terms. Now we will evaluate the constant terms here. In this case, Ex of xy equal to 0. That means at y equal to 0b, at the distance y equal to 0b, Ex of xy equal to 0, Ey of xy equal to 0 at the distance of x equal to 0a. And what are the a, b? In this figure, you can see that a is the length and b is the height of the waveguide. That means the length of the two sides of the rectangle. One is a and another one is b. Then in a similar process, by equating at Ex equal to 0, Ey equal to 0 and other steps, then we can derive that, we can derive the other equations like Exy, Hxhy equations for rectangular website. So in this figure, there is Ex equal to j omega mu n pi divided by k c square v, and to amn. Am and n are the values. The values are 1, 0, or 1, 1. These are respective values. By which by changing the values, we will get different modes like TM10, TM11 mode, and other steps. M and n basically denote the modes of the transverse mode. Then we get the propagation constant. Propagation constant is called beta. Beta is equal to root over. The formula for beta is equal to root over k square minus kc square, and the value. It can be kc square can be written as m pi by a whole square minus n pi by b whole square. So replacing this value with the kc, we get beta equal to root over k square minus m pi by a whole square m pi by b whole square root over. And m and n here are the values for 1, 0, or 1, 1, or whatever the mode we selected. And now we come to the cutoff frequency. In case of cutoff frequency, f of cmn, here mn also denotes the same thing. Cmn equal to kc by 2 pi into root over mu epsilon. Or then replacing the kc with the previous value, we can get this one. This one is the main equation. This one is the main equation for the cutoff frequency. So here it is written that at a given operating frequency f, only those modes in frequency f, only those modes having f is greater than fc will propagate. Modes with f is less than fc will lead to an imaginary beta, meaning that all the field components will decay exponentially away from the source of the excitation. Such modes are referred to as cutoff modes or evanescent modes. If more than one mode is propagating, the waveguide is said to be overmoded. That means in this case, if the frequency is greater than the fc or cutoff frequency, then it will propagate. Or if the frequency is less than the cutoff frequency, then that will yield the beta value as imaginary value, and that is why the exponential decay. There will be exponential decay of excitation, and that mode is called cutoff mode, and such kind of mode referred to as cutoff mode or the evanescent mode. And if more mode at a time is propagating, then that is called overmoded waveguide. The guide wavelength is defined as the distance between the two equal planes along with the waveguide. So the guide wavelength is defined by the distance between the waveguide. That means lambda z equal to twice pi by beta, and twice pi by beta is greater than twice pi by k or lambda. That means in this case we can say that the value of lambda In this case, we can say that the velocity, or this is mm, the equation of the wavelength for the waveguide, and this is the equation for the velocity of the waveguide. And we can see that in this case, we can see that in this case, the value of the velocity in this medium may be higher than the light. If the velocity which is greater than 1 by root over pi epsilon, that means the speed of light in this medium is greater than the speed of light. And then we come to the power equation, the power flow down. This is the power flow equation. The main power of the transverse electric in the 1-0 mode. In case of 1-0 mode, that means m equal to 1 and n equal to 0. In this case, the equation is omega mu a cube a10 whole square, which is the value of the constant term whole square, into b divided by 4 pi square, real value of beta. Then this is the equation for the power in 1-0 mode. So attenuation in rectangular waveguide may occur due to the electric losses and the conductor loss. Dielectric loss can be treated by making epsilon complex and using the general result given in equation 329. Conductor loss is the best treated using the perturbation method. That means using the perturbation method. In this case, this part says that the attenuation in the waveguide may occur in the dielectric loss or the conductor loss, and we can reduce the conductor loss by making by making the epsilon complex and using the general result. Then we come to the attenuation part of the. Then we come to attenuation part. The losses in the waveguide have the two sources, that is called dielectric loss and the conductor loss. In this case, the dielectric loss is derived by alpha d, and the conductor loss is defined by the term by the parameter alpha c. So this is the alpha c value, that means conductor loss. Alpha c value is the equation for alpha c is rs by a cube b beta k eta, and then 2b by a square plus a cube k square. So this is basically the alpha c mode, that means the conductor loss mode here. And then all these parts we have discussed here. This is all about the transverse electric mode. And now comes the transverse magnetic mode. The equation will be the same, like here that was the Hz value, and now we will analyze it with the electric field. And electric field, applying the boundary conditions here, we will get the similar kind of results here. Apply the boundary conditions here, we will get and derive the similar process in the similar manner, like we have did for the magnetic field for the TE mode. And now we are in the TM mode, and we will be analyzing the equation for the equation this one, and then applying the boundary condition in each time, we will derive all these terms, all these equations here. And then the propagation constant beta is equal to k square minus k square, like the previous one. And this figure is the attenuation of various modes. This figure defines the attenuation of the various modes here. So this figure actually plots the attenuation against the frequency for different modes in the brass rectangular waveguide with width equal to 2 cm. The y-axis defines the attenuation here, and the x-axis shows the frequency. And the curve of each line represents a waveguide mode, different kind of mode. Here TM11 mode, TM10 mode, TM10 mode, TE10 mode. So these are the different kinds of modes, how they are operates there. So the main observations from this figure is the attenuation varies by mode and the frequency. The attenuation, the value of the attenuation, that actually varies from the mode and the frequency. And then the sharp spikes occur at the cutoff frequency. In case of cutoff frequency, the sharp spikes, the cutoff frequency occurs in the sharp spikes. Sharp spikes occur in the cutoff frequency mode while propagating. And after the attenuation part, there is the mathematical examples and other steps, and the main summary of the results, the result of the equations that we have got there, all are written here, and we can memorize, or like we can learn the equations, or memorize the equation from this very chart. And after that, there is nothing else. There is the more different kind of mode. The TE mode 10, it can be 10. TE mode can be 20. And what is the cutoff frequency in each case? This is given in this chart. In this chart, there is the for different kind of mode, the cutoff frequency is given. And then this is the figure where the TE mode, the different modes, the figures of the different modes of rectangular waveguide are given, and the distribution, the wave distribution, the picture of the wave distribution are also given in this mode. So this was all about myself and the presentation of the rectangular waveguide. Thank you, sir. Thank you all.